Hello guys, welcome to my YouTube channel. I hope you all are fine. So let's start this video. The topic of this video is the design of checkered plate. Like we use checkered plate in the platform. So this is also like a sort of platform. So in which we are performing the analysis of checkered plate only. So let's start, guys. Yes. So this is the elevation view of a checkered plate platform. So there, like, it is a triangular base structure which is coming out from the tower, and it is supporting the checkered plate. And if we see from the plan view, it would be very clear. So this is the checkered plate which is supporting on these supports, which is coming out from the tower. So so we'll perform the analysis of this checkered plate. So like, make you clear that the analysis of checkered plate can be done only in, like, we can have to only done manually only, because in the stat pro, if you try to analyze it, you can only you can only find out their stresses, but you can't compare these stress with the permissible stresses, the actual calculated stress with the permissible stresses. So ultimately you have to analyze it in the Excel only or a manual process. So that's why I make that process completely manual in this Excel. So let's start. So first of all, there is a general detail. We have in the general detail, there is a dead load and the live load, and this is the load combinations. So I've considered the dead load and live load only. In the dead load, there is a self weight of checkered plate, and in the live load, there is a two human load I have considered with the tool and trackers. And in the dead load and the dead load and the live load, considered with the combination, and this combination in which 1.5 factor has been considered. This factor has been considered as per the IS code 800. This is the reference of IS 800, which is in this Indian standard, in which if we see the limit state of serviceability, so in that condition, if we go for the dead load and the live load combination, so first one can easily reflect to the dead load and the live load combination, in which there is a crane load, but we don't have any crane load, so we will consider this only. So in which there is a 1 factor, for dead load is a 1 factor and live load is the 1 factor. Okay, for the limit state of strength, for dead load 1.5 and for the live load 1.5. so according to which we have considered these factors. So this is the limit state of strength, yes, this is the limit state of serviceability, and this is the limit state of strength. And what is the input data? The input data is the thickness of checkered plate, the length and the width. This is the length and this is the width. Okay, so here which the cantilever span is 842.5 mm, and the yield strength of the material is 250 MPa we have considered, which is the mild steel, and modulus of elasticity of the steel, that is 2 into 10 raised to the power 5, which is also constant for steel. Spacing of the support is 1.215 meter, that is this length, and this is the cantilever length 843, which is equals to this. Okay, so we will analyze this like this platform by considering this as a cantilever span and this is as a simply supported span. So we will design the simply supported span, and then after that we will design the cantilever span. So our dead load is the density of the checkered plate. We have considered density of checkered plate is 7850, which is the density of steel, and the cell weight of the steel, which is coming out by the density multiplied with the thickness. So this is the weight, and the total dead load is, we have considered 3% just for the nut bolt condition we have considered. Okay, in the live load we have assumed 150 kg per meter square for the one human load with tool and tricycle. Generally the normal weight for any human who work at the height, they have a weight of 65 to 70 kgs, but we have considered some extra weight for the tool and tricycles, so we considered extra load, that is 150 load. So occupancy of the occupancy for the number of humans in the platform, that is 2, and the total live load will be 150 into 2. And the combination, first combination, that is dead load multiply by 1 and the live load multiply by 1. Then after that the dead load multiply by 1.5 and the live load multiply by 1.5. so this both criteria we have considered, and according to which we have converted this load by kilogram per meter square to Newton per mm square. So here we have calculated the UDL and the maximum bending moment for the simply supported span. As I told you, the middle portion from the for the length of 1250 we have considered simply supported, and the span 8430 we have considered as a cantilever span. So this is a simply supported span for which we have calculated the UDL. How we have calculated the UDL? The UDL we have calculated for the maximum load. We have considered the maximum load. The maximum load is 547.03 multiplied by the width, 1550. And the why I have multiplied by the width, because I have to calculate the UDL. That UDL have a unit of kilonewton, or sorry, kg per meter square. So sorry, kg per meter. So according to which I multiply by the width, so that load comes in which is distributing along the length. So if you found it difficult, then there is a conversion, simple conversion screenshot I have attached in this Excel, so in which there is a area load. So the way we have a area load, that is kg per meter square. This is something like that, the load I have. So if I have to convert this load into this load in the line load, so what I have to do, I have to multiply this S dash by the width, this width. So then I got the load S, which is distributing along the length. So my span was 1250, so I want the load which is distributing along the span. So what I have done, I have multiplied that area load by the width, and the width is J19, that is 1550. This is the width. See, this is the width, 1550. So now I have converted that load into Newton per mm, and here I have calculated the maximum bending moment. The formula for the maximum bending moment is WL square by 8, and if you want to see that, this is the formula, WL square by 8 for the simply supported condition. This is the simply supported condition. Basically there is a two supports and the load is distributing along the length. So in that case, this is the maximum bending moment formula. So this formula has been used, in which W into L square, L which is the length, 1.215. 1.215 is basically, this is the span length. So according to which the maximum bending moment has been calculated. So this is the maximum bending moment which is coming in the Newton per mm. So here we have calculated the UDL for the cantilever span. For the cantilever span, same thing, the UDL will be the same, because the width of our plate is constant, that is the 1550. That maximum load 547 multiplied by width 1550, that is 1550. So and here the maximum bending moment has been calculated, that is W into L square by 2 for the cantilever. For the cantilever beam, the formula for the maximum moment is, that is WL square by 2. That is the maximum bending moment formula. Okay, so here this load has been converted into Newton per mm square. And after that, after the calculation of the UDL and the maximum bending moment, what we have done, we have calculated the allowable bending stress. For the allowable bending stress, we have considered that 0.66 times the 250 MPa, which is our yield stress of the material. So what is this? J21, okay, J21, this is 250 MPa. So our allowable yield stress is 165 MPa out of 250. So now let's check for the thickness of the plate. For the thickness of plate, what we have done, this is the simple equation. Generally all the BTech student, like, they got to know with this equation. So m by I is equals to f by y. We have just only have to use this portion only. So here what we have did, we have equated this equation in the form of which, so we can calculate the thickness. So like if you see this thickness, so in which this is the formula, square root. How this square root has been done, first let hello, yes. So actually I have holded this video just to make the description of this. So in which what we have done, like, we have equated this equation in the form of which, so we can easily calculate the thickness T. So we have used this formula only, that m by I we have equated with the f by y. So in that case, m, we have a maximum bending moment, I is a moment of inertia, where b and h cube by 12 for the rectangular condition, because we have a plate. So that plate, like if you see the plate with the length of 1215 for the simply supported condition, and have a thickness which is 8 mm. So that thickness is this 8 mm, so which is forming a rectangular beam, so in which that is a moment of inertia, and whereas b is a width and h is a thickness. So and y is a distance of neutral axis from the edge, that is h by 2. So that h is also thickness, and f is a allowable bending stress. So the allowable bending stress is this. So I have what I have done, I have equated that T. I have put all this value together, but I haven't put the value of thickness, because thickness I have to calculate what is the required thickness I need to, what I have to provide for the allowable bending stress. Okay, so this is the allowable thickness we need to provide for the allowable bending stress. So this is what, so for in the case of simply supported span, so our thickness is okay, because we have provided 8 mm of platform, 8 mm of thick checkered plate. So but in case of cantilever portion, it required 11 mm thickness. So see, this is a platform, so if we provide 8 mm thick, suppose a person is standing there, so definitely it can easily bend. So somewhere that logic is very correct, so that's why it is failing. So now move further, like first we will see the check, and then after that, but we will change the values to make it safe. So now the next step is check for the deflection. In the check of deflection, there is a formula for the deflection, that is this. For the simply supported for the cantilever condition, that is WL ki power 4 by 8 into EI, and for the simply supported beam, that is 5 WL 4 by 384 EI. So this formula I had used for simply supported case. See, this is the bending moment formula for the rectangular beam, where this is the B and this is H is the thickness T, and I is a bending moment, that is B H cube by 12, and in this formula W we have a given, that is this, and L is a span 1215, and 384 is a constant value, E is a modulo of elasticity, and I is a moment of inertia. So I have calculated the value of deflection. The deflection is coming 22.7, that is very huge. So, and the allowable deflection we have, that is span by 240, So span is, we have 1215 divided by 240, so this is what. So now if this allowable deflection value is coming from IS 800, see this is the IS 800, in which at the table number 6, so in table number 6 these values, yes, this table deflection limit. So in which for the simply supported condition, for the simple span, for the vertical deflection, because we have a plate in the, like, that plate is in the horizontal position, and then this deflection will comes like this in the vertical direction. So this is a simple span, and we have elastic cladding and the brittle cladding. We have steel having elastic behavior, so span by 240, span by 240. So this is 5 mm coming. And for the check for deflection for cantilever span, in that case the same process, this is the W, and this is the B, which is the width of span, and H is the thickness, and the I is a moment of inertia, and E is a constant value, W is this. So we have equated this value in W, L give out 4 by 8 EI. So span, so the permissible value for the deflection, that is span by 150, which is coming from IS 800 from table 6, that is this. For the cantilever and the live load condition, vertical, so element not susceptible to cracking, element susceptible to cracking, so we don't have the condition because it's steel, doesn't permit the cracks because of elastic nature, so we will consider this span by 150. So span by 150, that is this span 843 by 150, so this is the value of deflection is coming. So now see our like this platform is like it is not safe in that condition, because that 843 mm plate is coming, like it is definitely creating a cantilever support, and that cantilever support is not safe. So we would like to make it safe. What we can do, we have to provide few supports from the bottom of the plate, so that it can like provide stability to this platform. So what best way we can do what, so this is the span. So what I will do, I will divide it in the in 3 parts for the cantilever span, and for the simply supported span, what I will do, I will divide it into 2 parts. So now let's check. So what, okay, still it is failing. It is, yeah, in the case of, in the both case it is like it's still failing with the minute value, with the very minute value it is failing actually. So what we can do, yes, now it is passed, okay, and the required thickness is also okay. So it is required maximum thickness for the cantilever portion 6 and the 4, but we will provide the uniform thickness we have already, so that is 8 mm thick plate. And suppose if we try to reduce the thickness 6 mm, what can happen? So in that case thickness wise it is okay, but in the case of deflection it will fail. So what we'll do, we will provide the 8 mm thickness of plate. Now what I have done actually, I have divided the cantilever span by 4, and I have divided the simply supported span by 3. So actually what I have done, I have distributed that span into 3 parts. So let me draw, and it will be clear. So this is how this 3 parts is, 1, 2 and 3. So these supports we have to provide, basically these bottom supports we need to provide, and for the cantilever span we need to provide more supports. One, two, three, four. So these supports we have to, and how these supports can be together, and these supports and these all support could be bind together in such a way. So this is how. So these bottom joist we have required, the members we have to connect to make it say, otherwise deflection, in the case of deflection it will not be safe this platform. So this is a simple design you can perform in this Excel sheet. Thank you guys, thank you so much for your support. Like if you have any questions you can put on the comment, and if you want that Excel sheet you can send me email, then it will be, and then I will send you that Excel sheet. So moreover maximum part I have cleared so that it will be easy for you to design it, because this is a very basic concept we generally study in the BTech during the type of colleges. Most of you very well understand that thing. Okay, and guys, one request I want, like if you are new at the channel, I request you please subscribe, because users, like I have started that channel in 2017, so I have posted 2 videos for the solar structures. So and after that I've got a support of 265 subscribers, and it is such a good thing for me actually, because I'm very new. So like if you guys support me, then definitely I have a lot of content to provide you, because I'm good in Excel, so I believe to do manual calculation rather than doing in softwares. I'm also like expert in softwares like StatPro and other robot Revit software. So I will also put this content, like if you support me. Thank you guys.